Yeah. So, why is quantum computing interesting? So, you people have been duped in thinking that it's something like very useful or something, or is it? Let's see. So, the thing is, quantum computers are, you can think of them as more accelerated, which would work very well for certain problems, maybe give super exponential speed up or exponential speed up, super polynomial speed ups and all. That class of problem we call PQP. So that's where quantum computers come in. Now, so those problems are, so this is one of the course which is more or less has become customary to show in any quantum computing talk. So the thing is like, if you see any problems related to simulating nature, so for example, you want to get into the drug design problem or design a better fertilizer or something like this, some quantum simulations and all. So those sort of problems using the classical computing model that we have, like that's not very viable. So, and yeah, we all know about Moore's law. So the speed is decreasing. But anyways, as I just mentioned, so there are certain class of problems which can't be anyway solved by classical computers. So to give a brief about my overview of my talk, I will not get into any specific techniques or anything in quantum compilers. I'll just try to give you a overall view of what the challenges are, and also like what are the work that has been done in quantum compiler domain and how it's progressing. So before like getting into that, we should first understand what a qubit is. Qubit is basically an analog of a classical bit. So how it is different? It's different because it acts as a quantum particle, okay, and it exhibits the quantum properties like superposition and entanglement. So this is a standard definition from Wikipedia. What a superposition is. For your case, what you can, for our computing specific case, what we can think of it is that at simultaneously both 0 and 1, those can exist, okay. So if you are given n qubits, simultaneously you can represent 2 to the power n number of states with that, okay. But what happens is there's a catch. So when you measure that, okay, when you measure that super state in superposition, you would just like converge into one state that is there. So that is the technicality, or you can say that is the magic we have to deal with to make quantum algorithms work. Same entanglement. Entanglement is something, let's say you have two electrons, okay, and those are entangled. The spins are entangled. We understand what, everyone of us, we understand, right, what electron spins are. So spin up, spin down, okay. So let's say two electrons are entangled with each other. So what would happen is, let's say we take one electron away from the solar system or as much distance we want, and then we measure one of the electrons. What would turn out is that if we measure the electron that we have with us, it to be spin up, then that electron that is arbitrarily far away from us, that would also turn out to be a spin up. Okay, so this phenomena is especially used a lot in the quantum networking domain. Now, this is a brief overview of like what a quantum program actually looks like when you like write it down in your computer using the SDKs that we have. So this is basically a part of a quantum kernel for a quantum support vector machine that I had written using Qiskit. So this RX gates, RX, RY, these are like some quantum gates that are there. H is basically the Hadamard gate. And those, these that you see, these are 2-qubit gates. So yeah, this is one thing about quantum computing. We have like multi-qubits as well. So as you can see, uh, the programming in quantum domain now at present, it's more of like writing code at a gate level. So you need to come up with a gate level kind of algorithms. So now let's come into what are the challenges in quantum computing. So the main challenge that is there. That's with the quantum hardware. So those are like very noisy hardwares, and also give us like very small amount of time to do the computation. This era we are living in, that's called the NISQ era, Noisy Intermediate Scale Quantum. And that's what Professor John Preskill of Caltech had coined this term. So the first 2 points, decoherence and dephasing, these are basically the qubit errors that can happen. Decoherence, you can think of like a bit flip. 1 became 0, 0 became 1. Okay. Dephasing is something more of, or like that's more of a quantum in nature. So basically, when you have when you have a state in superposition, let's say 0 plus 1. Now that became 0 minus 1. So the relative phase that's between them, that changed. So that's known as dephasing. Then like we don't have a standard ISA. There's a popular ISA or intermediate representation, however that's used, which is called like chasm. Then Intel has its own QUISA. Then Microsoft is working on its own ISA. So there are like different ISAs. Then there are different like hardwares as well. So some are working on superconducting qubit machines. Some are working on photonics. Some are working on some other things. And then there is a plethora of like front-end SDKs that you have. So like like working with all of them in a sync, like that is also one of the major engineering challenge, I would say. And like there are also many more. So there is no standardized architecture stack. We are living in an ENIAC era of quantum computing. So this is like one of the figures I borrowed from one of the papers by Margaret Martinus's group. So this is 1950s of classical computing. And this is the current, this is the 1950s of, yeah. So this is the ENIAC era, you can say. This is what we have now, a very defined architecture and software stack. And this is like the quantum stacks that we have. Like we have various things, compilers, optimizations, error correction, and all that. But yeah, there are no defined levels. So yeah, so there is a lot of challenge, but yeah, with challenge we get a lot of exciting work, right? So let's see. So here what you see, this is basically the IBM Sherbrooke QPU, Quantum Processing Unit. So this was around 1 month back when I like recorded its parameters. So these are all qubits that you can see, and these are the connectivity between the qubits. And this is like a few days back only. So lighter color means these are more error prone. Lighter color links means when you do 2 qubit gates between them, they will be more error prone. So as you can see, the fidelity of the gate operations, the links, the qubits, that also change with time, okay? Even when you do operations, so let's say you are continuously, you are doing some quantum thermodynamics or like experiment on your system. Like you are trying to solve some problem and you are using the quantum processing unit. And like let's say you are continuously applying the X gate, which is basically a NOT gate of, which is basically analogous to NOT gate in classical computing. So if you keep on applying that, what would happen is like the system would shift, and like the transition frequency that's in there, that would shift, so causing errors. So those sort of intermediate errors also come in. Now let's say you have an algorithm. So the quantum kernel that I showed you, that was a 3 qubit algorithm, right? So what you would do, what a quantum compiler would need to do is, let's say if you are given this sort of a chip, then it would need, there's a requirement for it to route it to the qubits in such a way that, so that the fidelity of the operation is maximum, okay? So you would want your logical qubits that you have in your program, those to be mapped to like physical qubits of higher fidelity, like this one or this one, this one. But again, there is one more challenge, one more catch. So when there is a 2 qubit gate that is there, so 2 qubit gate requires physical connection between the physical qubits. So if those qubits are not physically close, then there needs to be swap gate. So 2 qubit gates again like are the most error prone gates that are there. So we would want a fidelity of the order of 10 to the power minus 6, but that's currently we have an order of 10 to the power minus 3. So you would want to like cut down on your 2-qubit gate count as well. So those are the challenges that we need to work with. So for like solving for making the quantum compilers architecture agnostic, hardware agnostic, and like language agnostic, there is a compiler called Ticket Compiler, which is a pretty popular compiler in quantum domain. So they have come up with more of a LLVM-like approach. Okay, so where you see all these are, you can say like, I won't be overdoing it by calling them like DSLs for quantum compilers, quantum computers. So these are various dialects, and then the ticket front end that is there. So what it would do, it would convert them to ticket IR, and then there is the backend that would, like, based on the hardware architecture that is there, it would just compile for that architecture. So this is the component of the ticket compiler. So basically these are the front ends, backend means the backend machine that is there. So yeah, so let's say in your application you want to run the keyskit. What you just need to do in your Python notebook is just do pip install pyticket keyskit. So pyticket is a Python wrapper, a lightweight Python wrapper that's given over the main core ticket C++ library, which is written in C++. So once like the IR comes in and all, then the quantum specific optimizations that are there, that starts happening, like the gate count reduction, the routing and all that. And there are a plethora of quantum optimizations that are there. Then, as I said, like the hardware that we currently have, you can do operations coherently for them for, let's say, for just several hundreds of microseconds. So within that several hundreds of microseconds, you need to complete your computation. So like for that, like we can't do long calculations that we have, right? So with the devices that we have, we can currently work on a class of algorithms known as variational algorithms. These would look like very close to the classical neural networks that we have, feed-forward neural networks. So what I mean that is, like, these sort of Rx gate, Ry gates, or Rz gates that you would see, those are basically rotation about x-axis, y-axis, z-axis, and the angle of rotation is provided at provided by a classical optimizer. So just like you have neural networks, okay, they have certain weights, right? So when you are doing your training or when you are running your loop, the classical optimizer will determine the specific weights and then give it to the neural networks, and then we would see, like, that we're using the cost function, which parameter works well, and then we come up with the final model that is there. So that is what you can see here. So classical computer, in quantum computer, would run this parameterized circuit and also do the cost calculation, because that is a problem that is would take exponential amount of time if you want to do it in classical setting. So here we get like exponential speed up. So that's how like things happen. Now, for, as I said, like those hybrid quantum classical algorithms, the variational algorithms. So there we would have classical part and a quantum part as well, right? So if we let's say try to think it from a application writer point of view, okay, so the person who is coding the application, he would want to have a single source file where he can like code in all the instructions that he wants, and the compiler should be able to figure out what the classical part is, what the quantum part is, and do all the optimizations and run the loops and all that, right? So that's why the Intel compilers, the Intel guys came in. So they have an Intel SDK where the compiler they have written, like they have very well like separated out the logic and also like introduced various novel things there as well. So let's say you have your just 2 minutes. So let's say you have your C++ file, okay? So there, what they have done, they have introduced like a few quantum specific data types. So quantum kernels, quantum shared variables and all like this. So quantum shared variables are like the variables that can be shared between the quantum part and the quantum QPU and the CPU basically. So what happens is like this program that we write that gets into the front end. Front end converts it into LLVMIR, basically a .ll file, and then the quantum part extractor. Basically, the quantum part you write it in using a keyword called quantum kernel. So it has an identifier to it. So it separates it out. Okay. Then it gives it to the quantum device compiler. It does its compilation steps. It does the quantum optimizations. Okay. And they also provide a quantum intrinsic header which has all the definitions of the qubit gates that are there. And ultimately they come up with a quantum integration header file, okay, that has the function name, function length, and the parameters that are there. And then the classical part and the quantum part, those are woven together. Then there's a quantum runtime library that provides information, that provides functionality for communicating with the QPU and all that. And then they have a linker, okay, which converts it into a binary executable linkable format, okay. So that is so there we have like quantum basic blocks in that ELF format we would see. So I'll just skip this part as I'm short on time. So basically what happens is the CPU starts the execution with some random parameters. Then it does a blocking call, and the execution begins on the quantum part. The quantum basic blocks execute, and then sends the cost function, and it keeps on, it iterates. So basically, yeah, so this is also, so the classical program is computing the parameters, then it's giving to the quantum runtime library, and there is the quantum instructions that we have, and it's getting processed. I just want to take 1 minute to explain this ELFQ format, executable linkable format quantum. So here they have introduced these two blocks that are there, QBBS, basically quantum basic block section, and this one. So QBBS text, they should have the compiled compiled binary code of your quantum kernel that would be stored here. And this QBBS, this has a header, this has a table header file that has information regarding the quantum kernels that are there. So basically the linkages and the function size, the alignment and the offset and all. So the quantum runtime library that Intel provides, that would be able to, from this information, that would be able to decipher and run the variational algorithms. So so basically it's more of a repeating of history, because if you see GPUs and all, the NVIDIA GPUs are very good because they have the CUDA platform. So it's more of in quantum, the same thing is repeating. So don't be a mere spectator, you can be part of it. There's a lot of things that needs to be done. And you can find me in these platforms. With this, I'd like to thank you. And if you have any questions.
So I think the answer to this is much more opinion based, since you're working on this. How long till quantum computers make it to consumer hardware? How long till I can buy something and use it?
Yeah, so if you want to buy some quantum device, you can do it right now. I think there is a company called Quantum Brilliance that provides some artificial diamond based devices. But the thing is, what I understand, what you want to say is when you can have working
so
quantum
solving
computers.
problems that
Yeah,
I
solving
have.
actual real life problems.
Yeah.
So I would refrain from answering that directly, because I have seen very very seasoned people in this domain also don't understand. The thing is, let's say with what happened with AI is, someone said the model like AlphaGo, okay. So people knew that DeepMind was working on some such model which can maybe defeat a seasoned Go player or something like this. So when you ask the researchers of the domain, they would say that won't come in the next decade, but within 1 or 2 years that came in, okay. But let's now take nuclear fusion for example. Now that technology from 30 years, 40 years back, everyone is saying it would take only 10 years to come, but it's still not. We don't still have a way to do nuclear fusion. But yeah, so it's quite hard to comment on this.
Essentially waiting for a breakthrough.
But yeah, essentially waiting for a number of breakthroughs actually. But yeah, so if I just take the roadmaps that some companies have given, like IBM is very clear on their roadmap. So maybe within 7, 8 to 10 years, you can expect like if their roadmap is correct, you can expect some sort of practical problem solving quantum computers.
Hi. A really nice talk. I just want to ask how much time is it remaining to achieve the ideal abstraction for quantum computers? For example, when you showed the slides which contain the gates, right? I mean, that's not the ideal abstraction which a programmer who doesn't know quantum mechanics would work with, right? The kind of ideal abstraction we are expecting is, let's say in machine learning, you have all these compiler optimizations, you just add an annotation and you are through. You don't have to change anything. So let's say if I have a computation in mind and I just want to accelerate it on quantum hardware, uh, what's the research or what's the things going on that front where we tend to achieve that sort of abstractions where I just add one line and it just accelerates on quantum hardware?
So I just need a little clarification on your question. So what you are asking is like when like so are you asking like when we will get let's say some inbuilt library functions where we won't need to like compose a circuit, compose a algorithm like gate by gate, or you are talking about the optimizations that happens after that?
I am talking about, let's say, see this I may not comprehend, right? Because I don't know quantum mechanics.
Yeah.
So I even don't know what gates are and how to compose algorithms in
Right.
that sense.
Right.
Let's say if I want to compose an algorithm exactly in the ways I do it right now in our own conventional languages, right? In imperative or functional form, whatever. So how can or like what are the things which are done
Yeah,
on that front?
okay, I got your question. So basically, for certain problems that are there, like Shor's algorithm or Grover's algorithm, which are more known and which are more quantum in nature. So Qiskit, which is a distribution provided by IBM, they already give those like inbuilt library functions where you just need to call like import their library, call that function, and pass in the parameters you want to pass. So for Grover's algorithm, it's basically the number of iteration count that is there or the size of the problem that is there. Similarly for Shor's algorithm. So those are there. But for algorithms like variational algorithms, the thing is there is a hot topic of research, and these algorithms are built in such a way that you would need actually you would want certain some gate level at the gate level tuning. You would want to work at the gate level tuning, so you would want to like add your gates and all. But yeah, maybe you don't write a fully optimized circuit that can run on like which is optimized for running on the quantum processing units, but there are compiler passes which will do it for you. Okay, so if you don't even know like specific like what a specific compiler pass does, Ticket or IBM itself, they provide like optimization levels, level 1, level 2, level 3. You can just pass that and like they would do the optimization for you.
Thank you.